Hello and welcome to this session in which I will present and demonstrate the interoperability of VmWare's NSX-T with Alcatel-Lucent Enterprise's OmniSwitch. Here's the agenda. We start by introducing and comparing NSXT with NSXV. Then we talk about the Geneve encapsulation used by NSXT, which is different from VXLAN used in NSXV. We will look at a sample topology. We'll have a look at a few different hypervisor attachment options. Then we proceed to the demo and close with some key takeaways. Let's get started. I will not explain NSXT from scratch because that will take some time. I will assume that you have some knowledge of NSXV and I will compare NSXT to NSXV. And why do that? Well, NSXV, as you may be aware of, is reaching end of support, and so today we need to focus on the successor, which is NSXT. So let's do a comparison between these two products. Let's start with hypervisor support. NSXV is NSX for vCenter, that is for ESXi hypervisors only, whereas NSXT also works with KVM or even on AWS, etc. Then there's the encapsulation. NSXV uses VXLAN, whereas NSXT uses Geneve, and I'll talk about Geneve later in this presentation. Looking at bump replication, that is broadcast, unknown unicast, and multicast, NSXV can use unicast replication, but it can also offload replication to the underlay if the underlay is configured with PIM. NSXT does not use multicast replication. It only uses unicast replication. But as a recap, it is not flat unicast replication. It is hierarchical. Let me explain this with an example. Let's imagine we have a data center with 10 racks, and each rack has a topo rack or leaf node. Let's also imagine 30 servers per rack. The underlay is routed, and each rack uses a different access subnet in the underlay. Furthermore, let's imagine that the same VNI is extended to all 300 servers. In flat unicast replication, the source VTEP, that is the source hypervisor, would need to create 299 replicas. But that is not how hierarchical unicast replication works. In hierarchical unicast replication, for every underlay subnet, and that is for every rack in this case, and for every VNI, one VTEP will be chosen as the replicator node for that subnet. And so the source VTEP will replicate within its own rack, and it will send one replica to the replicator VTEP in every other rack. This replica will have the replicate bit set in the header such that the replicator VTEP will take care of replicating within its own rack. The result is that now the source VTEP will only need to create 38 replicas, not 299. And then each replicator VTEP will create another 29. Let's also remember that there's arc suppression, which is handled locally by the hypervisor. So we are not talking about a lot of replication, at least for ARC. Multicast replication in the underlay is optimal. However, it creates some dependencies with the underlay. The right multicast groups need to be configured, etc. And in multi-site deployments, it's quite possible that the network connecting those sites will not support or be configured to use PIM. Hence why hierarchical replication can be a very good option. Next, NSXV with the VXLAN encapsulation supports hardware VTEPs, such as an OmniSwitch, to create a layer 2 gateway function between legacy or physical workloads and overlaid ones, which is controlled through OVSDB for single pane of glass management from vCenter. NSXT does not support OVSDB or hardware VTEPs, and to my knowledge, no switching vendor has implemented as of today a hardware VTEP using Geneve encapsulation. The only way in which you can bridge overlay and legacy or virtual workloads is by going through an edge cluster, which is software and can be deployed either as a VM or on bare metal. Both NSXV and NSXT support distributed routing. In the case of NSXV, this is called the distributed logical router, and in the case of NSXT, this is called the T1 or T0 distributed router. NSXT has hierarchical routing in two tiers, where T0 is capable of interconnection with the outside world and can run traditional routing protocols such as BGP, but T1 is for internal routing only and does not run any traditional routing protocol. Another difference is that NSXV can do distributed routing for both VNIs and VLANs, but NSXT can only do this for VNIs. Another difference is the single pane of glass management, which in the case of NSXV is very tightly integrated into vCenter. You can do everything from vCenter and you hardly ever need to use the NSX manager, except maybe to do some maintenance tasks. But that is not the case of NSXT. In NSXT, you do all the networking from the NSX manager and you configure the compute from vCenter. And that is because in NSXT, you don't necessarily use vCenter because it could be KVM or something else. The last difference is that in the case of NSXV, which supports OVSDB integration for the layer 2 hardware VTEP, there is, or there was, a certification program for the hardware VTEP. NSXT does not use OVSDB or hardware VTEPs, and therefore there is no certification required for this feature. It can effectively run on anything that can forward IP packets. The underlay requires no multicast support, no Geneve support, no OVSDB support. It only requires IP version 4 forwarding and an increased MTU to accommodate the extra bytes in the Geneve header. So, about the Geneve encapsulation. It's very similar to VXLAN. It supports the same number of VNIs. It also runs on top of UDP. The main difference is that it includes an extra field for variable length options. And these options could be used for some use cases such as service function chaining, OAM, telemetry, etc. But to my knowledge, these functions have not been implemented on any shipping product as of today. The main reason why NSXT uses Geneve and not VXLAN is the hierarchical bomb replication, which I explained before. The source VTEP sets the replicate bit, and the replicator VTEP puts the source VTEP's address in this field such that other VTEPs, when they receive the frame, they can use that address to update their forwarding database. But wait a second, NSXV also uses hierarchical replication, which is very similar, yet it uses VXLAN and not Geneve. So how is it possible that NSXT requires Geneve for that, whereas NSXV does not? Well, it is possible because the control plane in NSXV and in NSXT is a little bit different. And without going into the nitty-gritty details, NSXT requires Geneve for this reason. Other than that, Geneve and VXLAN are equivalent. It's important to note that the ASICs in the new generation OmniSwitch 6900s support Geneve encapsulation. However, this is for the moment something to consider as investment protection because, as I said before, NSXT does not support hardware VTEPs or OVSDB. And this is similar for other networking vendors. The ASICs support Geneve. It's just that at the moment, there is no use case or reason to implement the software support for it. As of this recording, I'm not aware of a single networking vendor who has implemented Geneve support. So, the bottom line is that Geneve support in the ASIC is an investment protection feature for customer peace of mind, and that Geneve support may be implemented when a use case materializes. What we see here is an example of what I would call a typical underlay for NSXT using OmniSwitch 6900. It's a spine and leaf architecture which is 100% routed. All links are routed point-to-point links running OSPF, for example. Hypervisors in each rack would typically connect to a top-of-rack leaf virtual chassis through link aggregates. We will talk about hypervisor attachment in more detail in the next slide. Spine nodes do not need to be a virtual chassis. Each rack would normally use a different VTEP subnet, and this benefits bomb replication due to the hierarchical replication that I explained before. The access VLAN can be the same across all racks because it is only locally significant. It is not stretched in any way. and this simplifies configuration templates. Lastly, the VTEP addresses are assigned through the DHCP, and so we have the DHCP relay, which is also VMware's recommendation, by the way. Also note how we like the links that go from the spine to the leaf virtual chassis. This optimizes routing tables and reduces or virtually eliminates the need to forward traffic across the virtual fabric link. Let's now look at different options for attaching hypervisors to this underlay. The recommended option for hypervisor attachment is a virtual chassis with auto link aggregation. Virtual chassis virtualizes both switches at both layer 2 and layer 3, as well as the management plane, and it provides simple active-active load balancing. Plus, LACP is automatically configured. Note that most data center vendors do not support this, however. It's an advantage of AOS. Other vendors propose something like MCLAG, which is also known as MLAG or virtual port channel or even split model link trunking, etc. We used to have this feature in the past, and then we discontinued it because virtual chassis is superior. MCLAG or its other variations is always a proprietary feature, and it works in a similar way but slightly different for every vendor. The main difference is that MCLAG covers layer 2 only. It does not cover layer 3 or management. Now, this can create some issues, for example, with DHCP and DHCP snooping, because the request may go out one switch and the response may come back through the other one, and that tends to break things. It's also bad when deploying networking appliances. For example, a router such as an edge cluster or a firewall running a routing protocol such as OSPF. Because remember that OSPF uses multicast, and multicast traffic uses one link in the lag only, which means the adjacency is built with only one of the nodes in the MCLAG pair. So if the node or the link fails, then the routing appliance needs to discover the other node, build an adjacency with it, exchange routes, etc. The convergence time will be impacted. There is also the possibility of not using lag at all, which anyone could do. But remember that this is tunneling, and load balancing is done per address. So, from the point of view of the vSwitch, there is only a single address, which is the VTEP. So, in order to do some load balancing, you need 2 VTEPs now. It is more complicated. Both of these VTEPs, they need to be on the same subnet. I'm talking about the same underlay subnet. And that is because if the switch or the link fails, the VTEP needs to start using the other port. So that access VLAN needs to be extended across both switches. Now, this can be done with a cable, of course, but it's a pretty bad option because the moment you do that, you need spanning tree. And the whole idea of overlays is getting rid of spanning tree. Some vendors will propose creating an EVPN tunnel just for that, which does not require spanning tree, obviously, but EVPN is just another level of complexity for such a trivial thing. In OmniSwitch, you could create an SPV service that goes through the spines to avoid adding that connection. However, the bottom line is that the best and the simplest way is using virtual chassis. To summarize why virtual chassis is the recommended option, we can have a look at this table. It's automatic, it virtualizes layer 2, layer 3, and management. LACP is also automatic. There are no issues with the DHCP, there are no issues with routing appliances, it provides in-service software upgrades, etc. So that's about it for the introduction. Let's now talk about the demo. If you have seen my other NSXV demos, I'm using a similar setup here. I have a fully routed spine and leaf architecture using OSPF as the underlay protocol. I have a cluster of 4 ESXi nodes running NSXT, and I have 2 more ESXi nodes which do not run NSX. On one of those nodes, I have a VM, which we can consider a legacy workload. And on the other one, I have an NSXT Edge VM, which will do two things. The first one is to act as a bridge between the overlay and the legacy VM. And the other one is to connect to the physical lab network and exchange routes using BGP, so the overlay can talk to the outside world. Now, the logical view is similar to what I've used before with a classic 3-tier application. Each tier has one VM in each hypervisor running NSXT, and then there's a legacy tier which is associated to a VLAN and needs to go through the edge node in order to communicate with the overlay. We have distributed routing on the NSXT nodes. More specifically, that is a T1 distributed router. And then we have the edge node. The edge node is a VM, but inside there's different components which run like containers or somewhat similar to VRFs. The T0SR component can communicate with the outside world. And in this setup, it acts as the gateway for the legacy VM. And it runs BGP with the physical lab network, so both physical and overlay can communicate. The T1 router is distributed and the control plane runs on the edge VM, while the data plane runs on each NSX hypervisor as well as in the edge node itself. Remember that the T0 router is the only one running a standard routing protocol, BGP in this case. It injects an aggregate route to the physical network, and in turn, the physical network injects a default route. The T0 router, in turn, injects a default route to the T1 router, and the T1 router injects its connected routes. That's one route per tier subnet. Let's have a look and see it from both the underlay and the overlay. All right, let's review this from the NSX GUI. I'm going to start by going to System and Nodes. And what I see here are the 4 nodes which are part of the cluster which is running NSX. And on these nodes, I'm using out-of-band management. So this IP address is the management IP address. And what we see here is the VTEP IP address, which is connected to the underlay to the OmniSwitches that we saw in the diagram. We also have some edge nodes, and the first 2 are running on this same cluster that you saw, but I'm not using them in this demo. The one I'm using in this demo is the one at the bottom, the Edge 03, and this one is running on another cluster, which is also a vCenter cluster, but doesn't have NSX installed, even though it is running this VM, but it's just purely running as any other VM, and in fact, it could be deployed on a bare metal server or could even be deployed on KVM or Hyper-V or whatever really. So on this one, this is the VTEP IP address. So that's about what I want to show about the nodes. The next thing I want to show is something pretty cool, which is I think new in NSXT, and is the network topology. So this helps us visualize the overlay. So what we see here is that we have, well, firstly, we have these 3 segments. One for the database tier, which is an overlay segment, meaning it's using Geneve encapsulation. Then another one for the web tier and another one for the application tier. And in each of those, we have 4 VMs because we have 1 VM per hypervisor. Then those 3 segments are connected to a tier 1 gateway, and this one is doing the distributed routing for those overlay segments and is running on the Edge 03 node that I showed you before. And this one has a link to a tier 0 gateway, which is running within the same Edge 03. And so the difference between these two, as we said before, is that this one, the tier 1 gateway, takes care of distributed routing, whereas this one, the tier 0 gateway, and in particular the service routing component of the tier 0 gateway, can do communication either as a gateway, either as a layer 2 gateway, or routing with the physical network. And that's exactly what it's doing. So that's why you see 2 links at the top of it. Those two links connect to these two segments at the bottom. So one is border, and you see the traffic type is VLAN for this one because it's backed by a VLAN segment and not an overlay. And the other one is the legacy tier segment, which is also backed by a VLAN. Now, these two wires at the top connect to these two segments. We just don't see that connection because that connection is happening over the physical network. It's not an overlay, so that's why we don't see it. So let's review those segments then. So if I click here, we see that we have 5 segments. So we have 3 segments which are overlay segments, and they are the segments for the free tier application, web tier, application tier, and database tier. For each of those 3, we see that what's a subnet, and not just a subnet. In fact, what we see there is the IP address of the default gateway. That is the IP interface of the default gateway, which is in the T1 distributed router. We have 4 ports because we have 4 VMs connected to that segment. And the gateway is the tier 1, so that's the tier 1 distributed router. And then we have another 2, border and legacy, which are the ones that you saw in the previous diagram at the bottom right corner. And for those, we see that they are VLAN segments. We don't see any subnet and we don't see any port. And we don't see them here because, in fact, there are subnets and there are IP interfaces. It's just that they are not connected to the tier 1 gateway. They're connected to the tier 0 gateway service router component. There's nothing much to highlight here. It's all default configuration. The only thing really you have to configure is when you have a VLAN backed segment, you do have to configure that VLAN because that's going to go to the underlay. Yeah, that's about it. So let's now go and review the configuration on those tier 1 and tier 0 gateways. So let's start with the tier 1. So here it is. Let's edit. And I haven't configured much here other than route advertisement. And so the route advertisement is the only thing I changed is this. So I've set it such that those 3 connected segments, so the web tier, the application tier, and the database tier, are going to be advertised to the tier 0 gateway. And so the tier 0 gateway can then advertise it to the physical network through BGP. That's about it. So I don't have any service interface because I'm not running any service on this tier 1 gateway. Services, by the way, is things like firewalling or NAT or load balancing, things like that. I haven't defined any static route. That's really all that I'm doing on this one. The interfaces on this one, you already saw them when we saw the segments. Let's close this and let's go to the tier 0 gateway. So the tier 0 gateway, I have configured a couple of things here. So first is tier 0 gateways. So tier 0 gateways are the ones that connect to the physical world. They can run in either active standby mode or in active. But remember, this is connecting to the physical world. So there's no real magic here. So normally we run it as active standby, not active, because if we run it as active, then things, as you know, things like firewalling and NAT, they require session stickiness, they require symmetric paths, so they cannot really handle active. The only way you can do load balancing with that kind of service is by splitting different subnets and having an active for a group of subnets and a different active for the other group. So what I'm saying with this is, if you set this to active, essentially what you're saying is you cannot run any services. So normally you're going to set it to active standby. You can also have a VIP configuration. So we could use this, for instance, if I had 2 edge nodes, which I'm not using in this demo, but if I had 2, I could configure a VIP for the gateway interface for the legacy tier. So such that if one of these nodes fails, then I still have, another one takes over that gateway IP for the legacy tier, for the VM that's connected to the legacy tier. It's very much like VRRP. I have also some configurations here. So remember those interfaces that we didn't see when we were reviewing the configuration of the segments, that's because they're here. So let's click and have a look. So we have one, which is this one. And this is the one that I'm using for the peering with a physical OmniSwitch and running BGP. And then we have this other one, which is the default gateway for the VM, which is connected to the legacy tier. What else? So let's go to routing. So actually, I don't want to highlight anything from that. What I want to highlight is this. So in BGP, we're running the local AS number 65,000. It's on, and then I have one neighbor, which is the OmniSwitch, and that's the IP address of the OmniSwitch, and it's running this autonomous system, and the rest is all default configuration. So let's close out of that. Aggregation, yes. So, we have 3 tiers plus the legacy tier. And I could advertise one subnet for each, but really there's no need. Let's clear that. So there's no need to do that. If I advertise an aggregate route, as in this case, 100.100/16, that's really all I need to do. So that's what I'm doing. And I'm going to be advertising only the summary route. So we're going to verify this from the OmniSwitch letter. Also, we have some route redistribution, and let's have a look. So I am redistributing the routes that are connected to the T1 router and the T0 router. The ones connected to the T1 router are the web application and database tier, and to the T0 router is the legacy tier. So we are redistributing those routes such that they can be advertised through BGP. However, remember that I'm in fact aggregating, and I'm only advertising the aggregate. And then the other thing that I have here is I have enabled this because the OmniSwitch is going to inject a default route. And so with this setting, we're just going to accept that default route. So that's about it when it comes to routing. So next, let's have a look at this from the point of view of the OmniSwitch. And so I'm on the OmniSwitch. I'm going to start by reviewing the configuration. So we're going to do a show configuration snapshot BGP. So that's a configuration. It's very simple. I've defined the autonomous system number. I've defined my neighbor. I've also defined that I'm going to inject a default route. And then I've also configured BFT. In this case, it's not very useful because I only have a single connection between physical and overlay. But if I had more, then it would help improve convergence in the case of a failure. Let's now check the neighbor. So for that, the command would be show IPBGP neighbor. And there we go. So that's our neighbor. That's our H03 router. Our session is established. Next, let's see the paths that I'm receiving in this BGP table. So show IP BGP path. And other than this one, which is simply the connection between H03 and this router, the only path that I have is this one, and the reason is that I'm doing aggregation and I'm only advertising the aggregate route. So that's the /16 that we saw before from the NSXT GUI. What does it look like from the route table itself? So for that, we can do a show IP routes, and we're going to do pipe rep BGP. Because I have lots of routes on this switch, so let's better focus on the ones which we're getting from the overlay, and that's it. So this all looks good. The next thing we can check is the H03 VM, and the H03 VM, we have 4 routers in fact running on it. And the first thing I can do is get logical routers. And so we see that we have, well, in fact 5, because we have a tunnel that we're not using, and then we have 4. And that's because of what I explained before. So we have tier 1 and we have
tier 0, and tier 0 has a service router component which can connect to the outside, and it's what I'm using. I'm not using in this demo the DR component of the T0. What I am using though is the T1 router, and in particular the distributed component of the T1. So those are here. So the service router tier 0 is what I'm using to act as the gateway for the legacy tier and to connect to the physical network. And then I'm also using this one here, the distributed router, for the T1 router. And those are mapped to VRFs 10 and 9. Let's start with VRF 10, which is the one that connects to the outside. So VRF 10, not that, but this. And I can check the interfaces, so get interfaces. The output is not very friendly, but so if I scroll to the top, a couple of things to highlight. So firstly here, so this IP interface is the default gateway for the legacy tier. Then this one here is the IP interface that we're using for the BGP peering with the OmniSwitch. And then I have a bunch of other interfaces that are either default IP version 6 interfaces or some internal interfaces that are used for connection between the tier 0 and the tier 1. Because this one is the tier 0 and this one is capable of running a routing protocol like BGP in this case, but also OSPF, we can check the routing table. So for that, we can do a get route. We could also check the neighborship with an OmniSwitch, but we have already checked it from the other side. So what we see in this route table is, well, firstly, what we see at the top is the default route that the OmniSwitch is advertising. And we know that because we have a B, and this is the IP address of the OmniSwitch, and this is the default route. We also see a couple other things. So these three here, these three subnets are the web application and database tier subnets, and we see that they are connected to the tier 1 router. That means tier 1 connected. We have also this one here, which is similar, and it's the subnet for the legacy tier, but this one is connected to the T0 router itself. And then, well, we have this one, which is connected to the OmniSwitch, and then we have a bunch of other things, which are internal interfaces or IP version 6 interfaces, or so on. So let's exit out of this. And let's go to the other VRF. So let's do this, VRF 9. And this one is for the T1 distributed router. So for this one, we can still do a get interfaces. Well, we have this one, which is the default gateway for the web tier, and then if I scroll a bit more, so this one is the database tier, and this one is not this one, but this one is the application tier. Now, because this one is a T1 and it's not really running any routing protocol, I cannot run the command of get route, but I can ping. I'm just not going to ping because I think it's better to verify this directly from one of the VMs connected to the overlay. So let's have a look at that. So I'm now on the web of one VM. We're going to do a few pings to verify connectivity. We're going to launch a terminal. First, let's verify connectivity within this same tier. We're going to first start pinging ourselves. Verify that everything's good. So the next is the web02. It works. 3 and 4. So obviously everything works. Let's check the application tier now. And that works, and well, obviously the database tier works also. Then the next thing that I can do is I can verify whether I can connect to the physical network. So for that, because I'm, as you saw, we're running BGP with the physical network, we're receiving a default route. And in fact, in the physical network, I'm doing NAT out to the internet. Then I can simply launch a browser and see if we can visit our website. So www.le- like that, there we go. And clearly that works well. So what we see now is a VM, which is in the overlay, connected to the physical network through an edge router running BGP with the OmniSwitch. And then after that, we're going through a firewall, which is running NAT.
Let's now close with some key takeaways. The first one is that when it comes to the Geneve encapsulation, there is investment protection with hardware support in the ASIC, but software support on the switch is not required at this stage. It could be added later on if there is a use case that requires it. Second is to look at virtual chassis for hypervisor attachment because it is really the simplest and the most efficient of all options. And third is that this is an overlay architecture. The underlay is based on open standards such as OSPF, and we can use open standards such as BGP to exchange routes between the overlay and the physical network, and as you saw, this is pretty simple and it works quite well. That brings me to the end of this session on VmWare NSX-T and Alcatel-Lucent Enterprise's OmniSwitch integration. I hope it's been useful for you. Keep enjoying your Spacewalkers live event. I'm looking forward to interacting with you on this and other topics on the Spacewalkers platform.